So for this first question, it gives you a reaction, and the main things you need to notice are the fact that CCl4 are going to be made. Okay? This reaction is balanced. You're at 120 degrees Celsius, and you have 25.0 liters. So that's your volume. It tells you that you have chlorine gas, and it's initially present at a pressure of 0.40 atmospheres. So immediately, before I even consider this problem, I know I'm going to have to use PivNert. And I look at this first question, AI, and it says how many moles of Cl2 are going to be in this container. So I'm going to use PV equals nRT. I know my pressure and my volume. I know my temperature and my R. Remember, your temperature has to be in Kelvin. So this is the work they showed. You can also just plug into PV equals nRT. They actually just isolated N. And the answer you should get is 0.31 moles. Notice it's 0.31 because you need 2 sig figs. And so you get 1 point for not only the correct work, but then also supporting that work. So make sure that you're showing all of your work. For II, it says how many grams of carbon disulfide are needed to react with chlorine. Well, I know how many moles of chlorine are going to react. So in order to get into grams of carbon disulfide, I need to use my mole-to-mole ratio. I need to use stoichiometry. So I'm going to go from moles of chlorine into moles of carbon disulfide, then into grams of carbon disulfide by using the molar mass. And then the final answer I get is 7.9 grams because I want 2 sig figs. Now, you get 1 point for showing the correct mole-to-mole ratio. And then you get 1 point for the correct mass. All right? In B, it says at 30 degrees Celsius, the reaction is thermodynamically favorable, but no reaction is observed. However, at 120 degrees Celsius, the reaction occurs. All right? So this gets into why does the reaction rate increase when temperature increases? So let's read the question. In I, it says, explain how the higher temperature affects the collisions between the reactant molecules so that the reaction occurs at an observable rate. So remember, the higher the temperature, the greater the average kinetic energy. Okay? And the higher the average kinetic energy, the more collisions are going to occur. And not only that, but the more collisions with sufficient energy, with enough energy in order to overcome the activation energy. So not only do you have more collisions, but you have more collisions that have enough energy to overcome the activation energy for that reaction to occur. So in II, it says the graph below shows the distribution for the collision energies of reactant molecules at 120 degrees Celsius. And what it wants you to do is draw a second curve to show the distribution at 30 degrees Celsius. So remember what we've talked about this before, but when you have your energy curve, which I'll show right there, okay, the dotted line is what you're expected to be able to draw. So remember, imagine this is a piece of string. And by decreasing temperature, the energy of the collisions is going to decrease, which means you're going to have to push that piece of string to the left. Okay, so by pushing it to the left, what happens is the entire thing shifts to the left, number one. Number two, your peak is actually going to be higher than it was before. It's going to be less spread out. It's going to be more compact. And the last thing is that the energy right after it peaks, notice the curve is actually going to be, the new curve is going to be below the solid line curve. So when you get to your activation energy, the fraction of collisions is less. So notice the peak is higher, but then everything else after that point goes below where it would have been for the solid line curve. So you got 1 point for showing that the peak is above and to the left of the original peak. And then you also got 1 point for showing that the curve is going to be below the original curve beyond that activation energy. So notice how it's below it, not only after the activation energy, but then also before it as well. Okay. Now, if the energy were higher, remember, instead of going to the left and pushing your piece of string to the left, you would pull it further to the right. And so as a result, what that would do, your peak would be to the right. It would be lower than your original peak, but then everything after that peak would actually be higher than the original curve. All right? So those are all the different ways they can ask it. In C, it tells you that S2Cl2 is a product of the reaction, and it asks you to draw, in I, the Lewis electron dot diagram. So remember, you need to follow the octet rule, and this is what you should get. Okay? In II, it then asks you what the angle is going to be. Now notice really quickly before I go on to II, notice you get 1 point for simply drawing this, all right? In II, it asks what is the angle? Well, if you look back, you have 4 electron domains in your drawing, so as a result, the bond angle is going to be a tiny bit less than 109.5, so slightly less than 109.5. And so you would get a point for that because that's between 104 and 110. If you messed up an I and had the wrong drawing and had a different number of electron domains, the grader is going to grade this question based on what your drawing on I looks like. So if you had 3 electron domains and you had put 120 degrees for this question, that would be correct. So just because you get I wrong doesn't mean you're going to get II wrong. So in this question, it lets you know that CCl4 and HCl are going to be produced, and it says by cooling this to 70 degrees Celsius, CCl4 is going to condense while HCl remains a gas. So it says identify all types of intermolecular forces here. All right, so for HCl, I know that I'm going to have London dispersion forces and I'm going to have dipole-dipole forces. The other thing for you to note, since CCl4 condenses before HCl does, that means its intermolecular forces are actually going to be stronger because it is more willing to become a liquid than HCl is. So what can be inferred about the relative strengths? Exactly what we just said. The intermolecular forces for CCl4 must be stronger because it condenses at a higher temperature. Okay, so each of those was 1 point. Whenever you see anything about condensing and comparing 2 different molecules, remember it's going to be about intermolecular forces. And if it asks for all types of intermolecular forces, make sure you also always include London dispersion forces.